Welcome back. In this video I'm going to be making a simulation for the coefficient of pressure versus the angle theta as it flows over the cylinder. So first we're going to open up our setup. We're going to be using the same meshing from the project 3. So I won't be messing with any meshing today. Now the Reynolds number that I'm going to be simulating in this particular one is going to be 1 times 10 to the 5th. And the velocity is going to be 1.4607 meters a second. So once this opens, we already have our geometry loaded and meshing. We'll make sure that our solver is going to be pressure-based, absolute, steady, and planar. After that, we'll go to our models and make sure that our viscous model is going to be in K epsilon with all the default settings except for we'll add enhanced wall treatment and the pressure gradient effects. After this, we can close our models. We're not going to be messing with anything else. And we'll go to materials, and our fluid is air. Now for this one, we're also going to leave the default settings, so the density and the viscosity is going to remain the same. Close that. And next we'll go to our boundary conditions. So we'll start off with the inlet, make sure that the type is velocity inlet. And we're going to change our velocity magnitude to the 1.4607. And that way when you do the Reynolds number calculation, it'll come out to the 1 times 10 to the 5th. And nothing else, so we'll apply that. Close. And we'll double check that the outlet is pressure outlet, symmetry, symmetry, interior, and wall, of course. After that, we'll close the boundary conditions and move on to the reference value. We're going to be computing from the inlet and make sure that all these values are correct and carried over, like the velocity, for example, and the viscosity. Reference zone is going to be the surface body, so everything checks out. Next, we'll go to methods. I'm going to keep this on simple and presto. The rest of these are going to be the default settings. Now for our monitors, we'll change this to 1 times 10 to the negative 6 for all of these. Close monitors. Go to our initialization. Make sure that the hybrid initialization is 25 iterations. And then for the calculation, we're going to do 500 iterations as well. So we'll let that run, and then I'll pull up the post CFD. Perfect. Go back to the workbench, pull up results. Alright, so we'll true to the z-axis, and I'm unselecting these. I had this up, pulled up earlier. So this is what you would see when you first open it. And want to double check that it calculated the correct simulation. So and this one looks correct. I already added a pressure and a velocity contour. You can check out the last videos if you want to see how to do that. So we'll move on from there. And we'll go to click wall, which will be the inside portion of the cylinder, and symmetry 1, which is going to be the outside surface of the entire thing. And we're going to add location, a polyline, and we're going to name this the cylinder surface. Now the method you're going to change to boundary intersection. Boundary list is going to be wall, and then symmetry 1. And you know that you have these correct when it highlights the correct portions of the surface. And apply that. Now you have your surface cylinder, and what we'll do now is we're going to add some variables because I'm going to be comparing the coefficient of pressure and the angle theta as the flow goes over the cylinder. So we'll begin by adding expressions. So we'll do the coefficient of the pressure expression, and you have to define it. So this equation is going to be the pressure divided by, we'll do parentheses, 1/2 times the density, which is 1.225 in our case, times the velocity, which is 1.4607 squared. Close parentheses, apply, and it'll be in pascals. Now when you model other scenarios, you'll have to change the velocity according to the Reynolds number that you're trying to receive, and then you'll see the expression pop up here under your expressions. Next we can go back to variable, right click new, and add the coefficient of pressure. Leave expression, and then we'll do the expression that we just created. Apply that. Now you have CP as a variable. So we'll do this again for theta, starting off with the expression. Now the formula for theta will be a little bit different. You have to right click, go to functions, and CEL to find a cosine. Now it'll give you this bolded trig function. We'll do negative x divided by 0.5, and it wants you to have the units, so meters, and you'll know you did it correctly when it shows degrees after you hit apply. So you'll see the theta expression pop up in the list. We'll go back and add our new variable theta. Same thing, go to your expression drop down menu and find theta expression, apply that. So now you have your two variables that we want to chart. And the last thing we'll do is add our chart, name it CP versus theta. Same thing with the title. Our data series. Now the location is the only one, the cylinder surface. Next we'll go to the x-axis. We'll want this to be theta. There we go, theta. You can hit apply if you would like. Now you see this is pressure here, so we'll go to the y-axis and do the coefficient of pressure. And this looks more like what we're trying to get. So that basically sums up how to model the coefficient of pressure versus theta. Like I said, if you wanted to go ahead and change the Reynolds number, you'd have to change the velocity in your expressions for the coefficient of pressure. Other than that, it should be exactly the same. And that basically sums up this project. Thank you.